So today we're going to talk about torque. And if you remember, we're in the angular motion chapter or the angular motion unit. And we just finished up with kinematics, angular kinematics, which is dealing with the position. And remember, angularly, that's going to be our angle or our theta value. The velocity, which is in angular, the omega value or the change in that angle. And the acceleration, which will be the alpha value. If you remember, once we studied linear kinematics, we moved on into dynamics, which was really how do forces cause those motions, that change in velocity, that change in acceleration. Well, the same thing happens when we talk about angular, where we'll talk about torque now, which is going to be the force that is causing an object to rotate. Some key ideas is that force is like, so picture, if you will, this is maybe a hinge and a door, and you are putting a force on the door, pushing it upwards here or pushing it forward, which is causing the whole door to rotate from that. Notice that there has to be a certain radius that you're pushing at it with. So if I were to push exactly on the hinge of the door isn't going to go anywhere. It's not going to rotate at all. And so again, you're applying torque by putting a force on an object at a certain radius away. The units for that are going to be the units that are literally caused from that RF, which is going to be Newton meters. The symbol for torque is the tau, the Greek lowercase tau there. And then if you notice too, there is the equivalent of Newton's second law where we have F equals ma. Well, we have torque equals I alpha. So I is your inertia value, your moment of inertia that mirrors the mass's inertia. And your A is your alpha that mirror each other from that. So one of the things that we probably need to talk about then is, well, what direction is positive torque? What direction is negative torque? And this is going to follow the unit circle. So if we go counterclockwise, then it's going to be a positive torque. If we go clockwise, it's going to be a negative torque. So sample problem. Here's a static problem where the objects aren't moving. Two things that we need to keep in mind is that in these problems, all of the forces cancel out because it's not moving. And all of the torques have to cancel out too, again, because it's not moving. So when we look at it, maybe this is a seesaw problem. So the seesaw, instead of the pivot being put exactly in the center, maybe at a park they wanted to be creative and make it so that the parents could sit, not be exactly opposite and more balance it. So they put this not exactly in the center. You have one person sitting on one side of the seesaw with a mass of 45 kilograms. They are 2 meters away from that pivot point. Then you have another person here that is 68 kilograms. They are some X distance away from the pivot point. And then I put a dot here at the center of mass of the seesaw itself. So the mass of that seesaw is 12 kilograms and of that pivot board. And then the length of the whole board from end to end is, I don't know how I have kilograms there, is going to be 6 meters, is 6 meters. So find the normal force is going to be our part A here. And in that case, we can really look at, because we're dealing with all the forces, we can say, hey, all of the forces up have to equal all the forces down, which means that the force downward of this person plus the force downward of this person plus the force downward of the seesaw itself all have to be equal but opposite to the force upward of the pivot point, which we're going to call the normal force. So when we plug those values in, we can do 4.5 or 45 times 9.8, 68 times 9.8, and 12 times 9.8, and all of those have to equal the normal force, which would be 1,225 newtons. Now, the next thing we want to do then is probably find out, well, where exactly is this person sitting so that they are balancing out the seesaw so that the seesaw isn't moving up or down. So how far does the second kid need to sit to balance out the seesaw? And in that case, we're going to look at all the torques and say, well, all of the torques clockwise or counterclockwise have to equal all of the torques clockwise. So remember that torque is this force times a radius, So I'm going to take and say, well, this guy is going to want to make the whole thing pivot that way. If I make the fulcrum in the middle here be my pivot point, then this guy is going to want to make it pivot that way, and this guy is going to want to make it pivot that way. So I literally can say that the mass times gravity, because remember this has to be a force, so this is the force of gravity, times the radius is equal to this guy's mass times gravity and radius, the bars, and then plus the person's mass times gravity times radius. and I can look at that and say, hey, there's a gravity in all of those, so I'm going to get rid of those gravities, and then I'll have 45 times 2, 12 times, and notice that the center of mass here, if I divide this, is going to be 3, so it's going to be 1 meter from the pivot point, and then plus 68 times r. And when I solve, I get that they're going to be 1.15 meters. Now, because I made this be my pivot point, that 1.15 meters is from the pivot point. So they are going to actually be sitting, this is, I should probably put a thing here that says not to scale. They're going to have to be sitting really close to this 1 meter, right? 1.15. So another static problem that's a classic problem we would see is, hey, you go and decide that because of all of the snow and the ice that we've been experiencing, your parents say you need to knock all of the icicles off of the gutters so that we don't end up in the spring with all these floods overflowing our gutters. So you put a ladder out against the wall. So maybe this is the wall of your house. You know, that's your house. This is sitting on the ground in the snow. So those are there, and we would say, hey, what are the forces acting on it? Well, we have the force of gravity, we're going to say is 50 newtons. There's a normal force that the ground is pushing upward. There's also got to be a friction down here in the bottom that is keeping your ladder from sliding that way. You don't want it to slide that way. And then there is got to be a force that the wall is pushing on the ladder up here to keep the ladder from going inward, right? So there's a force that the wall is going that way. So again, remember, we can look at this. As long as this isn't moving, all of the forces are canceling out and all of the torques are canceling out. So since we have our forces here, let's go ahead and say all of the forces up have to equal all the forces down, and vice versa. All of the forces sideways have to the left have to equal all the forces to the right. So I'm going to say in the x direction, don't I have that this wall force has to cancel out the force of friction? And in the y direction, can't I say that the normal force has to equal the force of gravity, which we already defined to be that 50 newtons? So from there, if I want to find what does this coefficient of friction have to be in order to keep the ladder against the wall, I can say, remember, mu is the friction, the ratio of the friction over the normal force. I already defined the friction to be my wall, so I can substitute that in, and I know that my normal force is gravity, so I can substitute that in. Now, I run into a problem here because I know what gravity is, that's going to be my 50, but I don't know what that wall is, and that's why the second equation becomes very important, looking at the torques. So now I'm going to say, hey, all of the counterclockwise torques have to equal all of the clockwise torques, and that means I have to start looking at these in a different way. So how about we make this be our pivot point, because then it will cancel those two forces out, because the radius there will be 0, which means I only have two forces to look at now, the wall and the force of gravity. And there is one really, really, really important rule that we have to look at, and that is what was stated up here, that they always have to be perpendicular to each other. So what I'm going to do now is I've got to find the perpendicular value of that force of gravity, and I have to find the perpendicular value of the wall. Okay, so angle-wise, let's think through this. If this and this create a right angle down here, and this is 42, then doesn't this angle have to be 48? Which means if this and this create a right angle and this is 48, doesn't that have to be 42? And that's how I got that angle. Same thing up here. If this and this are at right angle, isn't this 48? And if this one creates a right angle up here, then if this is 48, doesn't this have to be 42? And if this is a right angle and this is 42, doesn't that have to be 48? So that's where I got those angles from. So the next thing I can do then is say that that wall perpendicular value times the distance or the length of the ladder has to be equal to the force of gravity perpendicular, that perpendicular one, times the distance or the length of that one, because this force is going to cause the ladder to want to rotate that way. This force is going to cause the ladder to want to rotate that way in opposite directions, right? Now, it looks like I forgot to put one very important value into my PowerPoint. It's probably going to show up here at the very end, and if it doesn't, that's okay. And that is that the whole length of this ladder, we're going to say, is 10 meters. So the length of this is going to be 10 meters. In that case, I can say W times the cosine of 48, cosine because it's adjacent to the angle. And then I can also say that the length will be the 10 there. Then I'm going to have the 50 times the cosine of 42. Again, cosine because it's adjacent to the 42. And notice that I only used 5 because I'm assuming that the center of mass of the ladder is in the very center of the ladder. So if the whole thing is 10 meters, then half of that is going to be 5. When I do that, I can solve for the weight to be 27.8. And what is our unit for, I'm sorry, not the weight, the wall. What is our unit for force? That unit is going to be in newtons, right? So then I can take and put my value of that 27.8 in for the wall up here and over 50. And notice that I get a reasonable coefficient of friction, because remember that coefficient should come out to be somewhere between 0 and 1 is normal. It can be greater. There'll be a lot of friction then. It can't be less. And so that looks like it could be a very reasonable value. So the next thing what we're going to do is we're going to move into kinetic rotation and talk about what happens if the forces don't cancel out and we end up with a torque that causes the object actually to rotate. Okay, so in the last part, we looked at static torque, which would be where all of the torques cancel out and the object is in static equilibrium. So the sum of the torques cancel out, the sum of the forces all cancel out. Now we're going to look at kinetic, which will be where the object starts rotating or moving. And we're going to start with that with a wheel and axle. So I have a wheel that's this big wheel on the outside, big radius, and then I have a small axle on the inside with a small radius. I would convert those into meters as my first thing I would look at there. And then I have a force that's acting on each one of those circles. So there's a force on the outside here of 9 newtons, a force on the outside here of 10, and a force on the inside here of 12 newtons. Notice in this case that all of them are perpendicular to the wheel. If they're not perpendicular, then we would have to find the perpendicular component in order for that to be, for us to solve this. So if I want the sum of the torques, then I'm going to literally take force times radius for each of those. And notice too that I followed the notation that we talked about earlier, that if we're going counterclockwise or following the unit circle, it's in the plus direction. If we're going clockwise or against the unit circle, that's in the negative direction. So I would take my 12 times 0.1 minus 10 times 0.25 minus 9 times 0.25, and I get a total torque of negative 3.55 Newton meters. Notice too, in this case, then that is what is going to cause this system to rotate, is that torque that's acting on that system. We have the units of Newton meters. That should look familiar to you. It was also our unit for energy, which is converted into the joules. But the difference is in a joule, that Newton and meter is in the same direction, and that's what causes you to have work done on the object. In this case, the force is not in the direction of the radius, and so no work is done, and that's why it's really not the same unit as what a joule is. So moving on then, let's take and apply this into something that we've studied before, like an Atwood machine. So here we have this Atwood machine. It has a certain radius of the pulley that's 0.25 meters. The pulley has a mass of 5. What I'm going to do is on one side, I'm going to hang a mass off of the end of that, and that mass is going to be 10 kilograms, and I'm going to let it fall until it hits the ground. So when we do this, remember that in the past we had to draw force diagrams. So we would say, hey, this guy has a force of gravity acting on it. This also has a tension in the string pulling upward. Up here, there's going to be a tension that is causing this to rotate. And isn't that the force then, kind of like over here that we said this 9 pulled it, the 10 pulled it, the 12 pulled it. So we're going to do the same thing with that. And we can look at it. What we have to do, though, first is we have to find the moment of inertia. So the moment of inertia for a solid disk is this 1/2 mr squared. You would look that up, or it would be given to you. We would have 1/2, the 5 is the mass of the disk, the 0.25 is the radius of the disk, and we can find that moment of inertia to be 0.156. Now, if I'm trying to find the tension, there are two different ways I can go about doing that. I can either look at this in terms of the angular, or I can look at this in terms of the linear, but I may have to look at it in terms of both, because remember, if it's not at static equilibrium, then I'm going to have to somehow put those two together in order to find that tension. So the first thing I'm going to do is I'm going to look at the angular part of it. I can say that the torque acting on the system is I alpha, which is the radius times the force. Now, can't I convert on the edge of the disk that acceleration is going to be the linear acceleration over the radius, which in this case I could write as an uppercase R? And isn't the force causing the rotation really the torque? And again, I could write this over here as an uppercase R also. And if I solve for the acceleration, thinking ahead, I don't know that acceleration, but I'm going to need a second equation to get rid of A in order to solve for T. And that's really where the linear equation comes into play. So I would have that my F equals ma, Newton's second law. I can say that the mass times gravity, which is the weight, minus the tension is going to cause it to accelerate. So can't I then simplify that and say, well, A is really mg minus t over m, and set the two of those equal to each other. So once I set those equal, then I can plug in my numbers and solve for t. So put all those in, square 10 times 9.8 over 10, and then solve for t here, and I end up with a tension that is 19.6 newtons. Now, the next thing we're going to do then is we're going to find the translational acceleration at the very edge or of this object, and we can literally just plug it back into the equation that we have here. So now that we have a t, can I plug it in and solve? And that's going to give me a value of 7.85 meters per second, and that's down in the corner there. I don't know if that's going to give it. It should be meters per second squared. Meters per second squared. Then the translational velocity, if I want to find out what is that linear velocity at that point, remember I can take and solve one of those. I can take and say, hey, the initial velocity is 0. As this falls, then it's going to fall with this acceleration of 7.85. Oh, geez. With that acceleration of 7.85, and then the distance that it falls, that height is going to be the 3 meters that we have there. And from that, I get that it has a final velocity once it hits the ground here of 6.86 meters per second. Then we can also prove this with energy. So, hey, isn't the potential energy that this has going to be equal to the kinetic translational energy it has as it's coming down, plus the rotational energy that the pulley system is going to have? So I can say mgh, 1/2 mv squared. My kinetic rotational energy is going to be 1/2 I omega squared. It mirrors the linear equation. Then I can plug in my numbers, mass, the gravity 9.8, the height of 3, mass of 10, looking for that velocity. The I value we found up here to be 0.156, and then this omega we can change and say, well, the linear velocity at the edge of the circle here has to be v over r, which will be v over r, and then square it. So that's where we get the r value, 0.25 squared, which I forgot my squared there. It should be squared. And then the next one, when we plug that in, solve, you should end up with the exact same velocity. And so that gives you an idea of what is going to be the kinetic value. So the next kinetic value that we're going to do is we're going to do an example of a falling rod. So I have this rod. It's at a pivot point up here at the top. Maybe this is attached to a rope or something, and then this will be a ceiling. So literally I'm taking the rod, if this is my pivot point, and I'm letting go, and the rod is falling and swinging because of it hanging at that pivot point. I can think through the fact that there's going to be a force acting in the very center of the rod as long as it's a uniform rod. That is the force of gravity, the mass times the gravity of the rod. And then I want to find the moment of inertia of that rod. So remember, we're going to do the integral of r squared dm. Then we'll take and use the line density. Remember that we said that line density is the dm over the dr. So I can solve for dm and plug in my dm, that's lambda dr. The next thing that we're going to do then is take and say pull out that lambda value. We'll integrate from 0 to L. We can start at 0 because it's pivoting at the end of the rod there. And then when we integrate that, we'll have lambda, which I can replace with the total mass over the total length, the r, 1/3 r cubed from 0 to L. And whenever we do that, we end up getting a 1/3 ml squared, which is the moment of inertia for a rod that's rotating around the end of the rod. Now, nextly, what we want to find is the angular acceleration. So we're going to use some kind of a torque because we have the force here. So remember, when we are talking linear acceleration, we would use F equals ma. So in this case, I have torque equals I alpha, which equals r times the force, the radius times the force. The I value we found is to be the 1/3 ml squared. The A is what we're looking for. Now the torque is actually happening at the center of the rod, so that radius will be L over 2, and then the force will be the mass times the gravity, which will be the weight of the rod. If I simplify that, then I end up getting the acceleration of the rod to be 3/2 g over L. Now remember that the acceleration that's the angular acceleration over the entire rod is constant. It's always that 3g over 2L no matter where you're at, because that L value tells you the acceleration at that point. So the next part then will be, well, what if I take and I attach an object at the end of the rod here? I look at the end of the rod. What's the linear acceleration at that point? And remember that to do that, we multiply times the radius or the distance from the pivoting. So the distance in this case will be the length of the rod, and my two L's will cancel out, and I'm left with 3/2 g. Now, if you think through that, isn't that kind of weird that the end of the rod is actually accelerating faster than the speed of gravity? It seems counterintuitive. So it's accelerating at 1.5 times the speed of gravity. So I have a video here that's from Harvard Science, and it shows you this. They'll show it to you in regular speed, and then they'll show it to you in slow motion. Once it loads, so this is faster than g. So you'll notice that they have this marble at the top at the end of the rod, and then they have placed a cup where it's going to fall. So when they pull it, notice that the rod is accelerating down faster than gravity, fast enough that it can catch the marble in the cup before the marble gets there. So moving on then, if we wanted to find what's the actual velocity at the end of the rod, we can take and say, well, hey, there's a certain amount of potential energy in the rod. And when the rod gets down to the straight up and down, all that potential has become kinetic rotational. So mgh, 1/2 I omega squared. We can plug in our mg. Our height is going to be, again, the center of mass, which at that case was the 1/2 L, 1/2 of I, 1/3 ml squared. And then our angular velocity is really going to be the velocity over the length of the rod. And so we can say that the linear velocity at the end of the rod is going to be that 3GL square rooted value of that. What if we wanted to find the angular velocity at the end of the rod, or the angular velocity anywhere? Remember, we can take and multiply that by the radius. And when we do that, we're going to solve for omega, and that's going to give us an angular velocity of the square root of 3g over L. Now, oftentimes what would happen is we would have started here and solved for omega, and then plugged in the omega over here to find the linear value. But I wanted to show you that there are a lot of times when we will actually substitute in this guy into here in order to simplify it, because our L's cancel out here whenever we do that. So the next thing what we're going to do then is we're going to take and look at an Atwood machine, like a full-blown Atwood machine. Okay, so for this last one, we're going to do an Atwood machine, kind of like what we did in the past. Now, remember in the past, though, we said this was like a frictionless, massless pulley, yada, yada, yada. Well, now we're going to throw in the angular motion of the Atwood machine, the pulley itself, in order to solve this as a more complicated problem. So first off, we're being asked to prove that I is 1/2 mr squared. Remember that to do that, we're going to say that I is the integral of r squared dm. Remember that for a disk like this, we would say that we're not going to go with lambda, because remember, lambda is the linear area. We're going to go with sigma, and it's going to be the change in mass over the 2 pi r dr, which is also going to equal the total mass over the total area later in the problem, right? So to begin with, we'll take that value, this guy here, and substitute in our dm. So solve this and substitute in. So we're going to have I is equal to the integral of r squared sigma 2 pi r dr. From there, remember that the 2 pi and the sigma are all constants, so we pull those out of the integral and do 2 pi sigma integral of r cubed dr. Now remember, this is going to be a definite integral. We're going to integrate from 0 to r. So I used a lowercase r here. I'm going to change that to be an uppercase R so that it's just different from this R here. So 0 to R. Then when I solve this, I'm going to have 2 pi sigma 1/4 r to the 4th, because the 0 term makes the second part of that go away. Now again, I can get rid of a 2 here and a 2 here. And so I end up with a pi over 2 times sigma r to the 4th. Now remember what we set up here, that our sigma value can really be this m over r squared. So I'm going to substitute that in and do pi over 2 m over pi r squared r to the 4th. My pi's will cancel out, my r squared will cancel out, and I'll be left with 1/2 mr squared is my moment of inertia for a disk like that. So there we just proved the moment of inertia is that 1/2 mr squared. Second thing that we're going to do then is, what is the acceleration of this entire system? Now remember, in the past we would have done 2 sets of force diagrams. So we're going to do that first here. I'm going to do a force diagram for this M1. Remember, I have the force of gravity pulling down and the tension pulling up. I'm going to say that there's a T1 here and the force of gravity. And then I can set up my equation that says, hey, if this whole thing is moving this way, then the mass 1 times gravity minus T1 is equal to M1A. Then I'm also going to set up another force diagram for the second mass. So I have the weight of the second mass, and I'm going to say this is T2. Now remember, in the other Atwood machines that we did where we neglected any of the circular motion, then in those we said that those tensions were the same. Well, we know now that in order for that to rotate, those tensions can't be the same, because the difference in those tensions is actually applying the torque on the system that causes the pulley to rotate. So if we set this equation up, if that M2 is going up, then I'm going to say that T2 minus M2G is equal to M2A. And since the pulley itself is rotating, then I can set up a force equation, or an F equals MA, so to speak, the angular equivalent of that for the pulley. So I can say torque is equal to I alpha, or RF. My I value we just set as this 1/2 mr squared. The acceleration that is going to be at the very edge of the disk is going to be A over R. And then the radius will be uppercase R. And the difference in the two forces is what's causing, like we just said, causing that pulley to rotate. So I can simplify that, and I end up with that equation. Now, the beautiful thing about this is, notice that we have three equations, but we also have 3 unknowns. Our T1, our T2, and our acceleration, all 3 of those are unknown. But because we have 3 equations, we can combine all of those into one. So here I just rewrote these equations, spreading them out to where I'm going to add them up. So this top one is the first equation. The second one is the second equation, and the one on the bottom here is the third equation, just rewritten to put the t's on the other side. And if I add it, notice what happens to my 2 tensions. So both of those cancel out, and I'm left with this equation that is M1G1, M1G minus M2G is equal to the sum of all of these masses, half of the big mass, and pulling out the A value. From there, I can simplify solving for A, so divide both sides by what's in the parentheses here, and then I can plug numbers in and solve, and we get an acceleration of 1.088 meters per second squared. Now, hey, where would we go next in this problem if you had to anticipate? Yeah, we're going to go back and figure out, well, hey, what are the tension values? Because now that we have A, can't we substitute back into these 2 equations to solve, or 2 of the 3 equations? So I'm not going to substitute this one because I have both of the tensions in it. But if I plug it back into each one of those individually, then that's going to give me the T1 and the T2. So I plug in my numbers back into those, and I get a T1 on the left and a T2 on the right. And then remember, that's what we said, that the difference in those forces is what's causing the torque to apply to the pulley and the whole thing to rotate the way that it is. So in summary, this circular torque motion that we have to deal with is, torque is a force causing objects to rotate. The symbol for it is that tau symbol, and the units are Newton meters, not to be confused with Newton meters that are our energy units. The equation that we're going to use is this I alpha RF. So I is your moment of inertia, alpha is your angular acceleration, R is the radius at where the force is being applied, and then F is the force that is causing the rotation. And keep in mind, those two have to be perpendicular to each other. And then the radius and force must be perpendicular to each other. So lastly, then, be sure to consider both linear and rotational aspects. So remember in that last problem where we did the Atwood machine, we have the two force diagrams that were our linear motion, but we also had the angular equation that used this that took into account our angular motion. And that, in a summary, in a nutshell, is what torque is.